Hey everyone, and welcome to This Explainer. Okay, today we are tackling one of the most fundamental, high-stakes problems in computer science and digital security. I'm talking about the digital trust dilemma. Imagine you need to exchange highly sensitive, incredibly valuable digital items with someone you absolutely do not trust. How do you guarantee a fair swap without either of you getting ripped off? And just as importantly, how do you do it without handing over all your private data to some central authority who might end up leaking it? Well, for decades, we've kind of just had to compromise. But today, we're diving into a fascinating academic paper that outlines an absolute game changer. It's called the Feud Protocol, and it actually solves this dilemma without sacrificing fairness or privacy. So, let's dive into our roadmap for today. We'll start with the digital trust dilemma. Then, look at splitting the trusted third party, move on to how FEWD synchronization works, talk about ensuring fairness and privacy, and wrap up with proving the protocol in Python. All right, part one, the digital trust dilemma, high stakes and zero trust. I really want you to keep this one fundamental question in the back of your mind as we go through this explainer. How do we actually exchange digital items fairly without exposing our private data to a central authority? You see, in distributed systems, entities, users, corporations, devices, they're constantly trading digital assets. But when there is zero trust between the parties, there's always this massive risk that one side is going to walk away with an unfair advantage. To make this concrete, the researchers gave a perfect real-world scenario. Picture a public health emergency. Hospital A and Hospital B urgently need to exchange clinical files to track the spread of a new virus. Now, these files contain highly sensitive patient data, stuff like IDs, lab results, medical histories, all fiercely protected by privacy laws. Because it's a literal emergency, they don't have time to set up complex legal mediation or hire a centralized authority, but Hospital A cannot risk sending their data unless they are absolutely guaranteed to get Hospital B's data in return. A leap of faith? Yeah, that just isn't an option here. Historically, solving this meant you had to make a tough choice. You could go with strong FEPS, which guarantees strong fairness so nobody gets ripped off, but they absolutely require a monolithic trusted third party, or a TTP. This middleman processes all the sensitive information, which introduces a massive privacy risk and a huge single point of failure. Or you could choose weak FEPS. These don't need a centralized mediator, but they only guarantee weak fairness. This means unfair results can absolutely happen, usually leading to disputes where human arbitrators have to come in and clean up the mess. So, centralized privacy risks or decentralized unfairness. Not exactly great options, right? Which brings us to section 2, splitting the trusted third party, the FWUD architecture. And this brilliantly illustrates the paradigm shift we're talking about. The traditional approach uses that monolithic trusted third party that handles literally everything. Deposits, verification, synchronization, release, it all flows through that one central hub. But the Feud protocol, which, by the way, stands for Fair Exchange Without Disputes, introduces a completely split architecture. It completely shatters that centralized mediator into 3 distinct pieces. 2 separate attestables that sit locally with the users, and 1 completely isolated public bulletin board, or PBB, which handles nothing but synchronization. This modularity, that is the secret sauce. So, what exactly is an attestable? Basically, it's a trusted execution environment, a TEE. Think of it like a highly secure, isolated vault embedded right into hardware or software, like ARM Trust Zone or Intel SGX. It guarantees that programs execute exactly as intended, completely hidden from the rest of the computer, and it can mathematically prove to anyone else that it hasn't been tampered with. So by putting in a testable on Alice's device and one on Bob's device, each person keeps unilateral control over their sensitive items, but they can still prove they aren't cheating. Moving on to section 3, how FEUD synchronization works, the 4 operations. The absolute crux of the FUD protocol is physical separation. The protocol physically separates manipulating the documents from synchronizing the exchange. All the sensitive stuff, encrypting documents, verifying files, releasing data, that happens exclusively inside those secure, isolated attestables on Alice and Bob's personal devices. The public bulletin board, it never sees a single byte of sensitive data. It only handles meaningless synchronization tokens. Okay, so let's walk through how an exchange actually happens. It breaks down into 4 core operations. First, deposit. Alice and Bob deposit encrypted versions of their items into each other's attestables, locking them up. Second, verify. The secure attestables secretly double-check the items to ensure they're exactly what was promised. Third, synchronize. The attestable sends simple text tokens to the public bulletin board saying, hey, we're ready to proceed. And fourth, release. If both tokens show up on the board, the attestables simultaneously decrypt and release the items to their new owners. Let's trace this out. For a successful exchange, Alice's attestable posts a token saying sync_A. Bob's posts sync_B. Both systems check the board, see both tokens are there, and boom, they release the documents. But what if it's canceled? Say Alice posts sync_A, but Bob decides to bail and posts cancel_B. When Alice's system checks the log, it sees that cancel token. Because the required paired sync tokens aren't there, both attestables just keep the documents permanently locked. Neither party gets the other's item. It's pure, mathematically guaranteed fairness. Section 4. Ensuring fairness and privacy, the formal model. Now, what's really interesting about this is how the researchers model the protocol using finite state machines. Basically, they mapped out every possible state and action for both Alice and Bob. They proved that there are literally only two valid end states for this whole thing: protocol success or protocol canceled. Because of how the public bulletin board is designed, it is mathematically impossible for Alice to land on success while Bob lands on canceled. They always converge on identical final states. If Bob tries to cheat, or if his Wi-Fi just drops, Alice's state machine automatically routes her to the safe, canceled state, and her data is totally protected. This brings up a really crucial concept: strong timeliness. This is the ability for anyone to immediately and unilaterally cancel the exchange before it's done, without waiting on the other person. In older systems, if the other person's computer crashed mid-transaction, your files could literally get held hostage in an endless waiting game. But with Food's strong timeliness, if Alice is tired of waiting for Bob, she just posts her cancel token to the board and safely walks away. Her data stays permanently encrypted on Bob's device. No harm, no foul. And we have to talk about privacy. The public bulletin board runs on standard RESTful APIs, but because all the sensitive document checking happens locally, the PBB is completely stateless and application agnostic. Guys, it's literally just a dumb database. It receives meaningless text strings like sync_A or cancel_B, and it just hands them back when asked. Even if hackers completely breach the board, all they'd find is a giant useless list of random words. The privacy risks you get with traditional centralized databases, they are completely neutralized here. Finally, Section 5, proving the protocol in Python. Just to prove this isn't just some academic fantasy, the team built a fully functional system using a very modern tech stack. They validated all the logical rules using the spin model checker and Promella formulas. They built the apps using Python and Flask. They used PostgreSQL for independent state persistence, and they packaged the whole shebang in Docker containers for portable deployment. So yeah, this is a robust, real-world implementation. And here is the definitive proof. We are looking at actual output from the spin model checker. These are called .trail files. They simulated every possible interaction, delay, and malicious dropout between the parties. It cranked out over 500 of these files, mathematically proving the system is 100% free of deadlocks or infinite loops. No matter what goes wrong, the math guarantees the system resolves fairly. You can really see the breakthrough when you compare Feud to legacy protocols from the 80s and 2000s. None of the old ones could do it all. They either sacrificed privacy for fairness, or they gave up on timeliness. Feud is the very first protocol to hit the holy trinity: strong fairness, strong timeliness, and absolute privacy, all without a centralized, synchronizing, trusted third party. It's a massive leap forward. But the implications here go way beyond just clever code. The researchers point out that this tech sustains swift trust theory in digital interactions. Essentially, organizations in supply chains or healthcare systems can now safely collaborate and swap critical assets instantly, even if they have zero history and zero institutional trust in each other. The math literally provides the trust. Which leads us to a pretty massive paradigm shift, and I want to leave you with this final thought. If we can now mathematically guarantee perfectly fair, perfectly private digital exchanges between untrusting parties without a central authority, what intermediary institutions in our society are no longer necessary? It completely changes how we think about digital trust. Thanks so much for joining me for this explainer. Keep learning, stay curious, and I'll catch you next time.